Hi everyone, and welcome again to the lectures on interactive media for this week, the second last week of semester, I believe. This week we're going to be looking at bitmap effects. So last week we looked at bitmapped images and we started playing with them and getting a sense of how you can manipulate individual pixel values to start changing an image from being color to being black and white. And sort of some basic effects like that. This week we're going to extend on that a little bit. What I would like to start with, though, and I would like to point you to this cool video. So, of course, one of the assignment tasks that many of you are doing is to create an interactive musical instrument, and some of you might have seen this around the traps. But there's a very cool marble machine by Martin Molin that I would recommend you have a look at. Not so much digital stuff going on there, although he does process the sounds that he gets out of his machines quite heavily, I think you'll see. But it's just a very cool idea that I thought might give you inspiration. So do check out that video and also the accompanying how it works video when you get a chance. So what we'll be doing this week: image effects, masking, and image filters, and then we'll be taking a very brief look at 3D, doing 3D and processing, and looking at basic 3D shapes and lighting. I should sort of give a bit of a disclaimer, I suppose. In this subject, we really only introduce 3D and touch on it. It is of course a whole area of you can spend your whole life doing 3D graphics, and there's subjects at UTS that look specifically at it. So we're going to be looking at it in like a week and a bit. So while you get a sense of how 3D works, and we're obviously not going to look at it in depth. So let's get started and take a look at masking. So in processing, you can use a mask image to sort of get detailed control over the transparency of individual pixels in an image. And what we're talking about here is when we have sort of two images layered on top of one another. The layer in the background will be obscured by the one in the foreground, but if you wish, you can set some of the pixels in the foreground image to be transparent, which will mean that you'll be able to see the background image through the foreground image. And in that case, the foreground image is acting as it's acting as a mask of the background image. So in processing, your mask image is basically a grayscale image, which means, in other words, as we've discussed previously, each pixel has a value from 0 to 255, with 0 being black and 255 being white. And if you have a mask image layered on top of another image at the back of it, where the pixel in the mask image has a value of 0, in other words where it's black, the corresponding pixel in the image that's behind it will be fully transparent, which means actually it won't be visible. And conversely, where the pixel in the mask is 255 or white, the corresponding pixel in the masked image will be fully opaque, that is fully visible. It's a bit hard to kind of conceptualize that, but it's much easier to see it with a demo. So let's take a look at that. So what we're going to do, let me explain what the demo does first up. We have this image here, colony.tiff. So this is a photograph that someone's taken of, I guess, some kind of bacterial colony or something in a petri dish, I guess. But it's just an image with of a dish with some stuff in it. So that's our background image. Our mask image is this one. So you can see it's black all around the edges, and in the middle, corresponding pretty much with where the petri dish is, the pixels are all white. So if we use this image to mask the other one, we should sort of, what we're hoping we'll see is all the contents of the Petri dish here, but we won't see any of the surrounding image. So let's open up our processing code and see what happens. So first of all, let's run it and see what the output is. So there you are, we're using the mask image to show only the pixels in the center of the original image. How are we doing this in code? It's really pretty straightforward. We've already looked at how to load images in processing, so this shouldn't be new to you, but we're declaring a couple of variables of type P image, one called IMG, one called MSK for image and mask. Then in our setup method, we're loading both images into those variables. So we're loading the colony.tiff, that is our Petri dish image. We're loading that into image, IMG, and we're loading our masking image into the MSK variable. Then all we're doing is setting the background of our window to be black and setting the size of the window so we can fit in the images. Nothing new there. And in our draw method, this is where I guess the magic happens. We're saying on the colony.tiff image, set the mask of that image to be the mask image that we loaded in. So that's it. It's one line of code which basically applies the mask to that image, and then we display the image on the screen. And again, to show you the result. So there's the result. Here's the original image. And let me open it. Original image, mask image, and the output of the processing sketch showing the original image with the mask applied. So again, to reiterate, wherever the pixels are white, where the pixels in the original image are fully visible, fully opaque, and where the mask image pixels are black, the source image pixels are invisible. That is, they're fully transparent and they're showing nothing but the background of our processing window, which, as we set in here, is black. So that's the basic concept of masking, and hopefully that's reasonably clear for you. And you know, that kind of technique, doing that kind of thing with still images can certainly be useful. But again, as with most things in processing, it gets interesting when you do these things dynamically, and often when you create masks based on user input, or maybe on some other incoming data stream, such as election data or data from Building 11, for example. So let's look at creating masks dynamically. So this might mean that we can mask out, if we want to, we can mask out particular colors in the main image. So for example, if we have an image that has a lot of sky in it, and we want to mask out the blue sky, we can do that with a processing sketch, and we can do it on any arbitrary image. Or we might say use processing drawing primitives to create a mask. So we might draw a whole lot of rectangles or ellipses or combinations of different processing drawing primitives to create a mask dynamically, to create whatever effect we like. So let's have a look at a couple of examples of that. And I should reiterate that these examples are all, of course, from the textbook, the processing textbook. I think it's chapter 10. Yeah, I'm pretty sure chapter 10. It's either 9 or 10, but I'll have to confirm that in class, I'm afraid. So anyway, let's look at an example here. Here we have, this example is image mask. And just to remind you as well, all these code examples are on UTS Online. Most of you would also know that you can download all the examples from the book website. I've given that link before in previous sessions. But you might find that some of these examples are not compatible with processing 3. There's a few minor code changes that need to be made to make it compatible with processing 3. But the ones I've uploaded to UTS Online, I've already made those changes. So the ones on UTS Online will work on processing 3, but the ones from the book website might not. Okay, so this example is working with this source image, a picture of a nice church somewhere in Europe, I would say. Let's take a look at what it does. So let's run the code first. And from looking at this, you can probably figure out that on the left here is the original image. In the middle is the original image with the sky masked out. And on the right here is the mask that we've created dynamically. And so we're using this as the mask on the original image to create the middle image, which is the original image but with the sky and clouds sort of sucked out of it. Let's take a look at the code. In setup, we load in the image, set the size of our window to fit the 3 images that we're displaying in the window. Then we're creating a mask image, which is it's basically a blank image. We're using this create image method to create an empty image of a particular height to store RGB values. Setting the background of our window to be black. You should remember from last time the load pixels method, so we're loading the pixel buffer on both image and mask images so that we can access the pixel buffer, which means we can manipulate each individual pixel value in some way. And then we're calling no loop so that we only call the draw method once. There's some commented out code here that it's not so important. Here is where the magic happens. So we have a for loop where we're going through all the pixels in the source image, starting with the first pixel going through until the last. We're getting the color of each pixel one at a time. And we're doing a little bit of maths here. If the red, green and blue components of the color of that pixel add up to more than 600, or if the blue component of the color is greater than 190, in other words, this is our algorithm where we sort of say, is the color of this pixel the color of the cloud, the color of a cloud or color of the sky? So is it blue or is it sort of mostly white? Then we'll say the mask pixel, the value of the mask pixel at this point is black. Okay, so we're creating our mask pixel to be black. Otherwise, the mask pixel will be 255. So we're creating, and then we repeat that for all the pixels in the original image. We're comparing and we're basically swapping any pixel which is sky or cloud will be made black. All the other pixels will be made white. And then we call update pixels on the mask image so that those changes that we've made to that mask image are actually saved in the image. We then display the original image on screen. We then set the mask of the original image to be the mask image that we've just created with our pixel buffer manipulations up here. We then display the image, the newly masked image, so that is the image with our mask applied, and we then display the mask on screen. And again, to reiterate, here's the output. So here, original image. We've done our processing, our pixel buffer manipulations to create a mask image that looks like this, all black, where the original image had pixels that were the color of cloud or sky, and all, well, actually it's all blue in this case because we're displaying it as an RGB image, but the pixels which are not sky or cloud colored are blue. They have the value of 255. Don't get confused by the blueness, it's not a big issue. The main point to notice here is that dynamically in our processing sketch we've created a mask image and we've applied it, and all the pixels in the original image show through where the mask image pixels are white or blue, and where the mask image pixels are black, we don't see any of the pixels in the original image come through. So a fairly simple application of masking to achieve a nifty effect of subtracting the background sky out of our image. And we could of course apply that code to any arbitrary image. Of course, depending on the colors that are in that image, it might have undesirable effects. If we want to subtract the sky, but in our image we have a swimming pool or some other scene with blues and whites in it, of course they would also get subtracted. So we would need to be a bit careful about that. Our algorithm is not that sophisticated, but you're hopefully starting to see the possible applications of masking in processing. The other example I will quickly show you is this pixel buffer mask. Again, let's run it. We're working again with our church as our source image. And this is the output. So quite a interesting effect, but it might not be totally apparent what's going on there. So let's take a look at the code and see indeed what is going on. Quickly work through. Our setup method loads in the original image and sets our window size. We set the background of our sketch window to be green. We call draw only once. And then in our draw method, we draw, if you look at this, we've got a for loop that counts from 0 to 2,999. And within that, we're simply drawing, well, in the for loop, we will draw 3,000 rectangles at random places on the screen, with a sort of of a random size within certain bounds. So I think the smallest rectangle there will be 5 pixels wide and high, and the maximum size would be 25 pixels height and width. So if we do nothing else, let me just comment out these 3 lines of code. If we do nothing else except run what we've got here, we should just see 3,000 rectangles on a screen with green in the background. So let's run that and just check if we're on track. And that is indeed what we see, 3,000 rectangles. I'm not going to count them, but you can you can pause the video and check if you want. 3,000 rectangles. The rectangles are white, and the background of the window is green. Okay, so far so good. So let's take a look at what happens in these lines of code. We load the pixel buffer, so that creates our pixels array containing all the pixel values of our image. of our processing window, not of the image. That loads the pixel buffer with the pixel values from our processing window. We then say the processing window image should act as a mask to that church image that we've loaded in. So those rectangles, those 3,000 random rectangles we're drawn, they should act as a mask on the source image, and then we simply display the image. So if you think about how masks work, there's our sketch window before we do any masking applied, and there's the original image. So we're going to take this image over here, the processing window with the 3,000 rectangles on it. We're going to apply that as a mask to this source image here. What we would expect to happen is that wherever there is white in our source image, we will see the original image. Where we have background color, we should see nothing. So let us run that. Make sure I take the comments out that I took out before, that I put in before, and let's run it and see what happens. And there we see, so wherever there's rectangles, white pixels in their source image, we see the original image. Otherwise, we see the background color of the processing screen. Hopefully, you see where we're going with that. So that means that, what we're doing there is using the processing drawing primitives to create a mask dynamically. One other thing I'd like to quickly show you is that the masking can get quite interesting if you start doing animations with it. So I've just loaded a different sketch here. This is pixel buffer mask animated. And it's almost exactly the same as the previous sketch in that we have this lovely church, and we loaded in and we set the background to be black. And in our draw method, which we're not calling no loop here, so we are using our draw method as we usually do. That is, it's being called 60 times a second, and in that we're drawing one rectangle every time the method is called, with a sort of somewhere on the screen with a certain degree of constrained randomness. We're loading the pixel buffer, and we're setting the mask of the source image to be the pixel buffer that we've just loaded. So in other words, that the pixel buffer, which is containing all the rectangle shapes, or each rectangle shape that we've drawn so far, and then we're displaying the image on the screen. So what we're hoping we'll see is where the background of the screen is showing through, where the background of the screen is black, where there's no rectangle drawn, we will see nothing, just blackness. But where every rectangle is drawn, we will see that little portion of the source image showing through. So let me run it to show you what we get. And as you can see, it's sort of like I don't know, kind of a montagey effect, where each time a rectangle is drawn, we're seeing a little portion of the source image, and eventually, as this runs for long enough, we'll see enough of the source image to see the to be able to recognize it. And of course, what's also going on here is that we have the outline of the rectangle, which is kind of creating an interesting effect. We could, of course, turn that off for a different effect, but I'll let you experiment with that in your own time or in the labs. Okay, so that is masking in processing, and hopefully from that you will now have a good sense of how you can use the masking technique in your processing sketches to manipulate images and use one image to kind of reveal or conceal another image. It's quite a powerful technique that you can do a lot with. So next up we'll be looking at filters.